So please, Alex, the floor is yours.
Okay, great. Let me make you full screen just a second. Okay, hello. So I'm Alex, and I like Homotopy Algebras, among other things. Thank you very much for inviting me, and may I say also for making this an afternoon conference, because, well, I'm somebody who usually sees the wrong end of morning, so this is very convenient. Right, so let's get to it. So what are homotopy algebras? Well, the answer is they are algebras you're familiar with, but generalized. So you break, for example, we know of exactly two kinds of algebras in physics, right? We know associative algebras, which are algebras of matrices, and the operation is matrix multiplication, which is associative. And we also know of Lie algebras, which obey the Jacobi identity. And I think these are the only two kinds that every physicist knows. So an algebra up to homotopy is what happens when you take either of these identities and you break it in a controlled way. So you introduce a differential d that squares to 0. And oh, now I can see my face again. Okay. Apparently that's normal. You introduce a differential that squares to 0 so that things that are d-exact under this differential d vanish. And then, since you have an algebra, you want to spoil the, say, Jacobi identity by an expression that's linear in each of the vectors x, y, and z here. And you also want, but however, you also want the Jacobi identity to hold if you hit the entire expression with a d. So you enter d and then this trilinear expression here. So this is called the homotopy algebra, or algebra up to homotopy, because the algebraic topologists who invented these things, well, they have nice theorems that tell them that if x is y plus dz, then x and y are homotopic if they're also d-closed. For physicists, for us, this basically translates to the notion of gauge equivalence. And we will see how this is made precise. Right, so I will focus on L-infinity algebras because so that's kind of the more universal formulation. For reasons that I won't have time to go into, the A-infinity algebras, so there exist theories which have both formulations, but for example, for gravity theories, there is apparently no natural A-infinity formulation, so I will stick to L-infinity. Okay, so this is the most important slide of the talk. We recognize an L-infinity algebra as, well, it's a thing that squares to 0, quite literally. So let's first cast Lie algebras in this language. So say you have a Lie algebra with structure constants C, A, B, C, and then you can express the Jacobi identity in terms of what I will call a BRST differential, which is also called Chevalier-Eilenberg differential in mathematical circles, and which takes this form. It's so you introduce these ghost variables C, which have ghost number 1, and I declare that variables commute or anti-commute depending on ghost number modulo 2. So the C's are anti-commuting. Then when you calculate Q squared, you get the Jacobi identity. It's a one-line calculation. And this here, d over dc, is a Grassmann derivative. So it anti-commutes when you move it past C's, as you would expect. So an L-infinity algebra is what happens when you generalize this to a Q operator, well, a vector field, or formal vector field, that depends on ghost variable z of any degree. They can be bosonic or fermionic, and which has a Taylor expansion around the point 0 that looks like this. So the Taylor coefficients are the structure constants of the L-infinity algebra by definition. And importantly, so this Q expression starts at linear order. So the first term here defines a bracket of one argument. That's just a linear map in the vector space where the L-infinity algebra lives. This term is familiar from the Lie algebra case, defines a bilinear bracket. A cubic term defines a trilinear bracket, and possibly up to infinity. So when you impose that this squares to 0, you get an infinite number of identities by expanding the result in powers of z again, because it's analytic. And you get an infinite number of identities. I'm not going to display them. But I will mention that the first of them, you can already see from this expression here, just says that the bracket of one argument, this d operator, squares to 0. So d is just, the bracket of one argument is just a linear map that squares to 0 and increases degree by 1. So in the L-infinity case, it's necessary to split your vector space into subspaces of definite degree, and then the brackets basically map. So the bracket of one argument will map a subspace of degree k to a subspace of degree k plus 1. So that's a definition. I'm demanding that this happens. Okay. So this is a good working definition of L-infinity algebras, certainly for finite dimensions, or if you can have a nice basis of it so that you can encode its structure constants, like you would for a Lie algebra. In infinite dimensions, you get in trouble, but for uninteresting reasons of linear algebra. But morally, this is the correct definition in all cases. Okay, so let's look at an example. Firstly, let's do the SU2 Lie algebra as soon as I move this out of the way. Good. The SU2 Lie algebra for... Sorry, I thought my computer was crashing behind Zoom, but I think it's fine. For SU2. So the Lie brackets of SU2 are... they famously have a cyclic symmetry. So T1 with T2 is T3, T2 with T3 is T1, etc. This is just the angular momentum commutation relation. And then if you read off the structure constants from these commutation relations and write down the Q vector field like this, then you get a very simple result in this case. You have three kinds, you have three ghosts, C1, C2, C3. Each of them are dual to each generator of the Lie algebra. And you have QC1 is C2 times C3, QC2 is C3, C2, etc. Now, so this is, you can take this as the definition of the SU2 Lie algebra if you want. And I will take this as the definition of the SU2 Lie algebra because I want to present a first example of an L-infinity algebra using it. Now, notice if I take C1, C2, C3, like here, and I'm assured that you can see whatever I'm pointing at. If that's not the case, somebody please interrupt me. So consider C1, C2, C3. If you hit this with Q, then you find it's 0 because Q will hit C1 and then it will produce C2, C3. That will square to 0, or else it will go right through C1, pick up a minus, hit C2, produce C3, C1, that will be 0, etc. So I'm bringing this up because you can use this fact to extend SU2 to an honest L-infinity algebra. So I have 3 ghosts originally, and then I add a 4th ghost of degree equals 2, just for book counting reasons. And I define a new differential Q prime, so that Q on the original ghosts is what it was before. And Q on the new variable eta is some constant K, real number, times C1, C2, C3. So for those that know about Chevalier-Eilenberg cohomology, you can get an extension by killing cocycles. So Q prime clearly squares to 0, because we only need to check that Q prime on eta squares to 0, and it is true because this right-hand side is Q closed. So we have a 4-dimensional L-infinity algebra, and the new element here is a non-vanishing 3 bracket, which maps, it's a 3 bracket, and it's just defined by a single structure constant, which involves all 3 generators, and the number k, which defines the cocycle over here. And this is, so we have thusly extended the Lie algebra of SU2 centrally, so the new generator Poisson commutes with all of the other ones. So there is no structure constant which is C, eta, down index, anything else. To an L-infinity algebra. By the way, sometimes I will say an L2 or an L3 or whatever algebra. Nobody uses these consistently, but they're all special cases of L-infinity algebras, and they just mean that most higher brackets vanish. So I'm going to call this an L2. And I think at least some people agree with me that this is an L2 algebra. And fun fact, you can find this, so this is actually closely related to West-Lumino-Witten theory through the SU2 Kac-Moody algebra that appears there. And if you want to learn more, you should read this nice paper, 2005, which interestingly, it predates the current craze on generalized global symmetries, which this is also related to. So this is actually a physically motivated example, but I won't go into the reasons why in this talk. Okay, so this is the second most important slide in the talk, which is why should we care? Why should we want this? Right. So the reason is that this meta theorem, which nowadays is an actual theorem, but I mean, morally, it's still a meta theorem because good luck understanding the proof, which is that every deformation problem, deformation meaning of a mathematical structure, like complex structures, which I will get to in a moment, has an associated L-infinity algebra, such that kosher or integrable deformations solve the Maurer-Cartan, correspond to vectors in the L-infinity algebra that solve the Maurer-Cartan equation. So this is a more or less obvious equation that you can form involving all of the brackets given a single vector in the L-infinity algebra. So here I demand that the vector lies in the degree 0 subspace. And if I do that, then the brackets will be symmetric because it's an argument of even degree. So this expression is not identically 0 in particular. And I should, now that I mentioned this, I should also mention something I forgot, which is that ordinary Lie algebras, as L-infinity algebras, they aren't concentrated purely in the degree -1 subspace in this convention. This sounds a bit nasty, but you win some, you lose some. Anyway, so if you wanted to guess how to produce this equation, you can get it by considering this, space of ghost variable, these z's, as well the coordinates on a manifold, and considering a translation by the vector v. So you look at the effect this has on the vector field q, and then the resulting vector field is defined in L-infinity algebra if and only if this equation is true. And the point of that is, so what this equation does more precisely is that it kills the order 0 term here. Okay, you can also generalize to things which have a constant term, but these are no longer L-infinity algebras, and in fact they are very nasty and are to be avoided. Right, so let's look at a simple and also classic example. Deformations of complex structures. So what is a complex structure? Basically, it's something that tells you when a function on your space is holomorphic. So the good way to deform this is to take the operator that tells you that a function is holomorphic, d bar, which is just an anti-holomorphic derivative wedged with a coordinate anti-holomorphic differential. And then a function that's annihilated by d bar is, well, it's a holomorphic function. So I deform the complex structure by shifting d bar to d bar prime, involving this mu I, which is a vector valued 1 form. And then this is a kosher complex structure if this d bar prime squares to 0. And you do a short calculation, then you find the Kodaira-Spencer equation, which is quite famous. It's also the equation of motion in type 2, 2B topological string theory, field theory. And this is an example of this general meta theorem, general philosophy. So you have an associated DGLA, which are some well, I forget which subspaces it consists of at the moment, but they are vector valued anti-holomorphic forms. And the bracket of one argument is the original d bar, the background d bar, and the bracket of two arguments is this nasty expression, which I wrote here. So, the moral of this story is when you look at a perturbation expansion, you find an L-infinity algebra staring back at you. And I will be returning to this point much later on in this talk, because it's actually quite physically relevant. So, as it happens, string theory is a very good source of L-infinity algebras, by which I mean proper ones, which are not Lie algebras. And they appear very prominently, originally, in fact, in string field theory. And they also appear, but less explicitly, mostly, as generalized global symmetries. And, well, I say there are some subtleties when they involve L-infinity groups, when it's L-infinity algebras. Sometimes you see L-infinity algebras that apparently cannot be integrated to groups. Well, let me not go into that. And they also appear a bit more explicitly these days in generalized geometry, DFT and XFT, which you heard, I think, Chris talk about yesterday, David talk about yesterday, and Dave talk about today. And they also appear in perturbative quantum field theory. And I will be talking about two instances involving these last two contexts. And intuitively, the reason why you have homotopy algebras in string theory is because strings and branes are extended objects. In fact, the higher the brane dimension, the worse, which is to say, the higher brackets you get in the L-infinity algebra. And we will see this very precisely shortly. By the way, I should say that if you do have questions and you don't ask me, then I will just continue talking. And this is a good place to ask me anything.
No hands for the moment.
Oh, somebody appeared? No, okay.
Please go ahead.
Hello?
No, we just wanted to say that you can go ahead.
Okay.
Go on as a question. No one has raised a hand. I'll put
Thank
something in.
Right, so let's see where they appear in generalized geometry, sort of following up on Dave's talk. You just saw this, so I will remind you that in type 2 supergravity in the common sector, or else in type 1, you have a metric and a B field, and they have gauge transformations corresponding to a vector, which is an infinitesimal diffeomorphism, and a one form. Like you can, well, yes, you can also have a closed two forms, but I will just stick to the one form here. And these act on the fields by the vector by the Lie derivative, and the one form just by shifting B by d lambda. And you can express this via the Dorfman derivative or else generalized Lie derivative. And it is this somewhat arcane expression. And the reason this is convenient, well, some of them were explained by Dave, but most importantly for us, the reason we want this is that it obeys a Leibniz rule. Which we will see in the, yes, right, in the next slide. So when you have two infinitesimal transformations parameterized, so big V is just a vector and a one form lambda, and big U is a vector U and a one form lambda U, and so on. They obey this Leibniz formula, but they do not form a Lie algebra because the Dorfman derivative is not antisymmetric. So if you had this property and this was 0, you would have a Lie algebra of infinitesimal generalized diffeomorphisms. But unfortunately, you do not. And in fact, I should mention here that you could consider taking the antisymmetric part of the Dorfman derivative, then you would end up with what is usually called the Courant bracket. And then what happens is that this property fails. So you can make it antisymmetric and break the Leibniz property, or you can make it obey the Leibniz property and break the antisymmetry. So the point is, these generalized vectors can be understood geometrically and algebraically as part of a, well, technically it's called a symplectic L2 algebroid, which was actually noticed by Reutenberg in 1999. And notice that predates the generalized geometry. History is non-linear like that. So, what do we need for an L-infinity algebra or algebroid? Oh, I forgot to mention, algebroid is, you can view this as just an L-infinity algebra, but where all of the structure constants here, they all depend on space-time position in a smooth manner. And the space-time positions are embedded inside the space of these ghost variables in degree 0. So that will be our working definition of an algebroid. The actual definition is a bit more painful, but you know, we're physicists. Actually, this is good enough. So I'm telling you that the irrelevant Q with Q squared equals 0 that reproduces this Dorfman derivative is as follows. So you have your space-time with coordinates x mu, as is traditional. Then you introduce a set of fermion coordinates. You introduce these psi's, which correspond to dx, where d is the Dirac derivative. These are coordinate differentials. And you introduce these he's, or chi's, which basically correspond to, which vaguely correspond to the interior product by the coordinate vector field, d over dx. And you also introduce a conjugate momentum p to x, which satisfies the usual Poisson brackets. And you let p have degree 2, so it's bosonic, so this is still an ordinary Poisson bracket. But the fermionic variables, you declare them to have degree 1. And you declare the bracket to be a super Poisson bracket, so that the Poisson brackets of odd elements are symmetric. Okay. So you can view this as the fact that psi and chi under the Poisson bracket are each other's Grassmann derivatives. So with these degree assignments, the q that has q squared equals 0 and gives you an L-infinity algebroid is this very simple expression. So qx is psi, or okay, I have drilling upstairs, so I can be hang on. Right, so qx is psi, which is the coordinate differential, as I just advertised. And q psi is 0, which is the same as d squared equals 0. And you also have identities involving chi and p, which you need in order for q to be a Hamiltonian vector field. Okay, and you can see from these identities that q squared clearly is 0. Right, so what is the point of this? Well, you can embed generalized vectors in this supermanifold as functions of degree +1. So these will be linear in psi's and chi's, and a term linear in chi is obviously a vector field, and a term linear in psi is obviously a one form. And then you can do a two-line calculation and find the Dorfman derivative inside this bracket expression. So the Dorfman derivative of v prime along v is just the Poisson bracket of qv with v prime, which is an expression also known in the maths literature as a derived bracket and was invented by Kosman and Schwarzbach. And so the point of this is, well, this has a lot of very nice features, chief amongst them the fact that you can just use the super Jacobi identity for the Poisson bracket to prove the nice identities here, in particular the Leibniz identity. And in fact, the proof of the Leibniz identity is extremely general. If you know that your Dorfman is given by this expression, it will just be true. So closure is guaranteed. So that's a very good practical benefit, and you also have a few theoretical ones. Right, so you can also, so in this L-infinity algebra, you can also encode the infinite dimensional L-infinity algebra of gauge transformations in the supergravity, which are basically lots of commutators of derived brackets. Now, for this particular example, most of these will vanish if you go to a big enough bracket. And, quartic and higher ones will vanish if my degree counting is correct. But for, say, exceptional generalized geometry, you will get lots of higher things. And right, so this is, if my counting is correct, again, this is an L2 algebra. Actually, no, there is a reference for this, which I forgot to insert in the slide. It's Rothenberg and Weinstein. So you get, so the generalized vectors actually form an infinite dimensional L2 algebra. And I say infinite dimensional just because you have an infinite number of vector fields on a vector bundle, which this essentially is. So just in algebraic terms, it might be infinite dimensional, but it's about as complicated as the central extension of SU2 that I gave you a few slides ago. Now, say we want to accommodate an H-flux to make a point I will be explaining shortly. Yikes. So you can accommodate an H-flux by deforming these Q along P and P. So by degree counting, you know Q of chi must be degree 1 plus 1 equals 2. So, and you also need a free index. So this is the natural thing you can write down. And then you can just deduce whatever you need to make Q squared to 0 here. And you get this derivative. So this is the same as a twist of the generalized Dorfman derivative by an H-flux, which appeared, I think, in Dave's lecture. And in fact, I like to argue here that this is exactly the same flux seen by a probe string. So consider a cylindrical world sheet. So you have time R and then space is S1. Sorry, there's just drilling everywhere. I don't know what's happening. And then you couple this you couple the cylindrical world sheet to the 3 form by pulling it back to a 3-dimensional manifold whose boundary is the cylinder. Right, so if you do that, say you do that, and you want to do, you want to consider the phase space or Hamiltonian formulation, you introduce momenta for your positions that describe the string embedding, and well, that's it. So these are the canonical string Poisson brackets. You have probably seen this. And this here is the contribution that the Wess-Zumino term makes to the symplectic structure of the string. And there is also a vanishing XX Poisson bracket, which I didn't write. Now, the claim is that you can form these one-form currents. So these are linear in the momenta, P. So the momenta are naturally one-forms, which are then dualized into tensor densities, scalar densities of weight 1. And then X prime is is the component of the one form dx on the spatial sections S1 of the world sheet. So if you form currents linear in P and X prime, where prime is the S1 derivative, sigma, d over d sigma, then as we saw with the linear in fermions business here, you can accommodate a vector and a one form. And now the claim, and this is a slightly complicated calculation, is compared at least to the two ones I have just given you. The claim is that the twisted generalized Lie derivative actually appears in the Poisson brackets of these one-form currents amongst themselves. So it appears in the ultra-local term that determines the, let's say, classical closure. And there is also a Schwinger term that depends on the ODD structure of the generalized tangent bundle, but I'd like not to consider that. So it appears in the non-anomalous term. So for example, if you had these one-form currents that generate a closed symmetry algebra, and they correspond to an isotropic subspace so that this term drops out, then their closure is governed by the Dorfman bracket, but including an H-flux twist as included in this prescription here by the blue terms. Okay. So there's a very close connection between the algebra of gauge transformations in generalized geometry, which is to say supergravity, and what happens on the brain. And this story actually generalizes to M theory, because there are L-infinity algebroids for the M2, which came, is that 20 or 30 years after the, no, that's 12 years after the F1 story. There's ones for the M5 and D3 brains, and if you have a favorite algebroid brain, I can probably write one down for you. And they correspond to the Dorfman bracket relevant for exceptional generalized geometry, as Dave or Chris mentioned. And the general pattern is, if you have a P brain, it corresponds to an LP plus 1 algebroid, which means that a bracket of, a derived bracket expression like this, which has more than P plus 2 elements, automatically vanishes. And the reason for that just has to do with how fluxes enter into the algebra of Dorfman derivatives. Now, so this is a very nice story that works very well if you don't double or extend any of your coordinates. If you want to do XFT or DFT, you have what people call pre-L infinity algebroids, which is just to say q squared is not equal to 0. And well, you should read these papers to learn more about them. I don't really understand things that don't square to 0. And there has been lots more work involving L infinity vaguely in the context of the gauge structure of generalized geometry, supergravity, extended geometry, and so forth, including some work on the XFT, the tensor hierarchy or the tensor hierarchy algebra, which is, I'm mentioning this here to underline that this is an L infinity algebra. It does square to 0, and it has extended coordinates at the price of being very infinite dimensional. And you can do a few more things involving, say, topological field theories. And there has also been lots of related work on Leibniz gauge theories, which are morally and also actually closely related because they have canonically associated L infinity algebras. Although it's not yet clear to me to what extent the distinct prescriptions for the associated L infinity algebras are fully compatible in all of the cases. Okay, that's about everything I wanted to say with regard to L infinity algebra structures in supergravity and generalized geometry and that sort of thing. So
Alex,
unless there's any...
you still have about, let's say 15 minutes.
Ah, good. I should be able to get through it. Right, so let's talk about the L infinity algebra structure, but in field theory. And I'll stick to classical field theory for this talk and just make a few comments about quantum field theory in the last slide. So this is actually a very old story, but it only appears to have been picked up in the general physics community, or for some low values of general, relatively recently due to this paper by Olaf Holm and Barton Zwiebach in 2017, which kind of explained these ideas again and slightly generalized compared to, say, the BV picture, for example. And there's a general dictionary that associates an L-infinity algebra to a field theory. And say you have a very simple case where you have a gauge symmetry that's irreducible, and then you have a vector space which is graded, and then in each subspace you have, in degree 0 in my conventions, you have a space of fields, and then in degree -1 you have a space of gauge transformations. Again, this is analogous to the how Lie algebras are embedded in L-infinity algebras. As I mentioned before, Lie algebras are to be found in degree -1. And so that's not a coincidence. And then you also need another space here to house for the equations of motion to map things into, which can be identified with antifields in the BV formalism. And fun fact, you don't need a space of antifields for the gauge fields, for those of you who know what that means. You can read this paper, which, well, they just constructed the L-infinity algebras and didn't need them. So I guess they're pre-symplectic. Those can be pre-symplectic in a different way.
No,
Yes?
sorry, maybe I jump in very quickly. So in this field theoretic construction, there is no any difference with the standard cochain structure behind, right? So this is really BV cochain that you demonstrate here.
The standard what structure?
I mean, cohomological structure, the chain that you form.
Yes.
Or there is something else I should know.
No, the only subtlety here is, well, I didn't mention the brackets. So the one bracket here is the linearized equation of motion and gauge transformations. So if you're familiar with string field theory, that's analogous to the worldsheet BRST operator.
Yes.
Good. And then the higher brackets are just n particle vertices.
Mm-hmm. Good.
Okay. Right, so let's do a simple example. So I will focus on an example without gauge symmetry here. In part because I did gauge symmetry in the previous half of the talk in a lot of ways. So you can take sine-Gordon theory. You have a two-dimensional scalar field, and this box is just the usual, I'm using mostly minus here. And you have an infinite series of interaction terms. So you don't have a space of gauge fields, and you also don't have a space of ghost antifields. So you have your space of fields, which are just scalar functions in 2 dimensions, and the equation of motion multiplet, which is the same space, but just now considered in degree 1. And then I declare the bracket of one argument, D, to be just the Klein-Gordon operator. So it maps a scalar function V0 into the space V1 and hits it with the Klein-Gordon operator. And then on V1, it's just 0. So then this clearly squares to 0. And then I get all of the odd brackets by my counting, which depend on the coupling constant beta, and the power is 2k plus 1. And the bracket vaguely looks like a pointwise multiplication of the scalar functions. Now, if you're worried about such things, and apparently you should be, you can make the scalar functions here lie in Schwartz space of functions of rapid descent so that this product makes sense. So this example is nice because it's, well, lots of people have seen this before, and they will agree with me that you need an infinity of brackets even if you don't have gauge symmetry. So in this case, the L-infinity identities are satisfied quite trivially, but you don't have, so sorry, I'm getting tired. The point is you can have a complicated bracket structure regardless of what the gauge symmetry is doing. And the other point I want to raise was that consider the cohomology of the D operator, the linear bracket. So this means things that are annihilated by D modulo things that are D exact, like this. So you can prove, if you've picked a correct space of scalar fields, like the one I just mentioned, that this cohomology consists of on-shell fields, fields that solve the Klein-Gordon equation. These are the things that appear in S matrix elements, okay? This will be important in a bit. Now, I can just write the irrelevant Q with Q squared equals 0. I need formal field variable phi of x and a phi star, and it looks like this. And because Q phi equals 0, we see that Q squared equals 0 very trivially. But for gauge theories instead, Q squared equals 0 is equivalent to gauge invariance, or if you like, tree-level ward identities. Now, if you take the brackets that you read off from this expression and you form the Maurer-Cartan equation, well, there is only one thing you could possibly get. You get the equation of motion for a scalar field. So recall here in the Maurer-Cartan equation, the vector v must lie in degree 0, which I identified as the space of fields. And then the D operator is the Klein-Gordon operator, and then the brackets correspond to the higher vertices, and they enter with powers of beta here. So with respect to the meta theorem I mentioned before, the L-infinity algebra structure of classical field theory is the one that describes, well, the perturbation theory of the moduli space of classical solutions, or classical vacua, if you want. And I should say that if you had a gauge theory instead, you need a quotient modulo gauge equivalence to obtain the moduli space, exactly as you would expect. And I will also mention here, because I forgot to do so originally, that if you want to dot all the I's and cross all the T's, the Maurer-Cartan equation needs to, well, it can explode because this is not a formal equation because V is an honest vector. So sometimes you need to tensor your Lie algebra with a ring that's nilpotent, so as to make the thing terminate. And so then sometimes people speak of Maurer-Cartan functor or deformation functor. It's something that maps a nice nilpotent ring, well, Artinian technically, to Maurer-Cartan moduli spaces. And if you know how that thing works, you can actually construct formal solutions. Anyway, that's some mathematical fine print. Right. So now I wanted to impress upon you the importance of equivalences of L-infinity algebras and how they correspond to equivalences of, well, physical theories. So the fundamental observation is that you can have theories with different Lagrangians, different field content, which can nevertheless have the same solution space. For example, you can take any Lagrangian, because we're working classically here, and you can introduce a pair of new fields, pi and b, and just add them in like this. Now, this has the same solution space as the original Lagrangian because the pi equation of motion will set b to 0, and the b equation of motion will set pi to 0. If you like the BV formalism, these come in as trivial pairs. So the question is, how can we see this at the level of L-infinity algebras? And this is something that L-infinity algebras are very good at. So you can have criteria that tell you when distinct theories have the same solutions without having to integrate things out explicitly. as for this example. So to do this, I need to introduce the notion of mapping or morphism between L-infinity algebras, which is, well, it's a collection of linear maps from one vector space to the other, and they take any number of arguments in the original vector space on the left-hand one. And I will only need to focus on the very first map, that is just an honest linear map from V to U, and takes one vector and spits out one vector. And the identities that tell you the morphism respects the brackets, they also tell you that phi1 is sort of equivariant with respect to the differentials on each of V and U. So that's the only one you need to look at. I'm bringing this up because phi1 will always map things which are annihilated by dV onto things which are annihilated by du. So it descends to a map on d cohomologies. So, and rather non-trivially, we arrive at the notion of homotopy equivalence for, or quasi-isomorphism of L-infinity algebras. So the criterion is very simple, at least if you work over real numbers or complex numbers. If not, God help you. The criterion is that phi1, this linear bit of the morphism, just induces an invertible map of cohomologies. So in physics terms, this means that your morphism can't kill anything that is on shell, but otherwise it can do whatever it likes. And then there's actually not a very hard theorem, at least this proof, I don't find it very hard, by Kontsevich in '97, that says that if your L-infinity algebras are connected by a quasi-isomorphism, then their Mark-Cartan moduli spaces, so these modulo gauge equivalents, well, they're isomorphic. They're the same manifolds, or formal manifolds, or groupoids, if you want. So this is very nice because we can actually just check this very directly, and then we don't need to care what the morphism is otherwise doing. So of course, the example I gave you is an instance of this, where phi1 just kills the new fields. And the reason is, well, this is difficult to explain without doing a big calculation, but if you have seen the BV formalism before, the reason for this is that pi and b do not contribute to the cohomology because they come in as trivial pairs if you add their antifields. If that doesn't make sense to you, then because pi and b have trivial equations of motion, the pi equation of motion sets b to 0 and vice versa, then they don't actually contribute to the cohomology of the d operators, the analog of this, but for the big Lagrangian here. Okay, so this is a basic example of elimination of auxiliary fields that is captured by the notion of quasi-isomorphism. But there's more, and two of these are very, very physically important. For example, the calculation that takes your tree-level theory and gives you tree-level scattering amplitudes, that is also quasi-isomorphism. And this has an avatar in the L-infinity picture. There's a unique L-infinity algebra structure on just the cohomology of the L-infinity algebra under its differential that I just gave you, which is quasi-isomorphic to it. So this means that any representative that's homotopy equivalent, you can pick, you calculate the S matrices, you're going to get the same result, well, isomorphic result. And intuitively, the L-infinity structure on the cohomology actually does look like a bunch of S matrices because let's look at the brackets. The brackets will map a bunch of vectors in the cohomology to the cohomology. So as we saw for the sign-Gordon theory, this cohomology is spanned by on-shell states. So this looks like an amplitude where if you have n arguments here, they get mapped into, so n part on-shell particles are mapped into one on-shell particle. So it's an n to 1 amplitude or an n plus 1 point tree amplitude. And somewhat more generally, you can pick a subspace of effective degrees of freedom that contains all of the on-shell states. And if you then integrate things out, you have quasi-isomorphic L-infinity structure. And you can actually check that this agrees with what you would get from the path integral. Well, the tree level path integral in this case, because we are working at tree level for the purposes of these slides. And this last one actually illustrates the major difference from the BV formalism, which is that here you can play around with non-locality. There's nothing here that makes you be local. And in fact, this is a bit by design, because these L-infinity algebras were originally discovered in string field theory, which is also non-local. And this is exactly what you need in that case. Yeah, so this is a major difference from the BV formalism, where if you allow for non-localities, you can transform any theory into a Newtonian particle, if you really want. Right, so I hope that I sort of illustrated, well, maybe not illustrated, but at least plausibly argued that this homotopy equivalence of L-infinity algebras could be taken as a definition of duality between distinct theories. Right, so how much time do I have? I don't think I have much time. So I will just say that the current frontier, as it were, consists of quantum generalizations of this picture. If you're doing perturbative field theory, then to go quantum, you do a path integral, you integrate an action S, and out comes, say, a 1 pi effective action. And then you have two major complementary quantum generalizations. You can either have a homotopy algebra corresponding to what goes in the path integral, S in red here, which deforms the algebraic structure. You get a loop or quantum L-infinity algebra. Or else you can have a homotopy algebra corresponding to what comes out of the path integral, which I prefer because it is my baby, in which you keep the same algebraic structure but deform the ground ring to capture all of the H-bar corrections. And right, so the first, the one related to the integrand, is closely related to the quantum BV master equation. And that's why the algebraic structure is deformed. It's because of the difference between the quantum and classical BV master equations. Whereas in this picture, where you keep the same algebraic structure, you have an L-infinity algebra because you have the Zinn-Justin equation, which is, well, it's a thing that squares to 0 that just captures all of the ward identities, gives a general formulation for all of the ward identities. And it turns out that it's natural to identify that as the Jacobi identities of an L-infinity algebra. And I think I've run out of time, so I will stop here.
Thank you very much, Alex. That was a very interesting talk. So I was told that Anton, you had a question.